In the previous videos, we talked about the inverting op-amp input, inverting configuration with a reference voltage, something like this. We have a op-amp, and it's we call that V minus. That's the input voltage to the non-inverting input to the op-amp, and V out R1, R2, and we discussed the situation when we have a reference input or the non-inverting side. So it's very easy to write out the transfer function for this configuration. There are many ways to do this. We have a quick ways, just let everything, all the input outputs, everything refers to the VR, the virtual ground. So that means V minus the input, we turn that V minus to minus VR, and VR minus VR here, that's 0 volts, and V out minus VR, okay? When you reference everything, all the voltage into the VR, rather to the real ground 0 volts here, then you can just quickly write out the transfer function for these configurations, okay? Because now if you have a 0 volts here, okay? 0 volts here is a typical non-inverting configuration. So that means V out minus VR equals minus R2, R1, the ratio between these two resistors, and the times V minus the input voltage minus VR. Okay. So this is very easy to write here. Let's erase stuff we write here because we already have the transfer function now. Now, if VR is a virtual ground, it's a voltage, you can set to basically any value you want. And what's the easiest way to set these VR values? We can set VR. The quickest way is by two resistors called resistor divider. Resistor divider to set this. Okay, so that means we have a resistor divider like this to the ground, and this is your VR. And now we have another input is V plus, because this is the input to the non-inverting side of the op-amp. Look this configuration now. This configuration, if you can see 4 resistors and with the op-amp. If you know, this is a very typical configuration, very popular. It's a differential op-amp input. Okay. So what's the transfer function looks like now? If we have 2 resistors here, R3, R4, then VR, what is VR? VR equals V plus divided by R3 plus R4. That's the current flow through this path. Okay, then the VR equals just times R4. Okay. Basically, we could just put VR into here. Before that, let's rearrange this one into a better, easier to understand format. So we have V out equals minus R2, R1, V minus plus R2, R1, VR plus VR. Okay, we just distribute this into the bracket here and move VR to the other side. Okay, so V out equals minus R2, R1, V minus the non-inverting input plus 1 plus R2, R1 VR. Okay, now let's plug the VR into here. So V out equals minus R2, R1, V minus plus 1 plus R2 R1 VR, which is R4 R3 R4 times V plus. Okay. Okay, this is the transfer function AV, the differential op-amp. This look like a lot of going on here, a lot of stuff here, but we can further simplify this. Okay, we have some special situation. What happens if R1 equals R2 equals R3 equals R4, they all equal R. Okay, what's that? Then the V out equals, this is ratio is 1, so it's minus V minus input plus, this is 2 times 1/2 times V plus. So V out equals V plus minus V minus. Okay. So what that means, if we back to here, can we write, let's erase the stuff here. If all the resistors are the same values, we got V out equals V plus minus V minus. That's the difference amplifier, right? So V plus minus V minus, that's the difference voltage between the input and these two inputs, it's delta V. So okay, so you can see V out equals the difference between these two inputs, and there's no common mode voltage. You only see the difference voltage, okay? Because the common mode voltage, for example, if V plus is 7 volts and V minus 6 volts, the common mode voltage is right here, which is 7 plus 6. Divided by 2 is 6.5 volts. But here, V out equals 7 volts minus 6 volts equal 1 volt. So it's only the difference, no common mode voltage. So that's just one way, very typical way to remove common mode voltage. Then if you remove the common mode voltage and only keep the difference voltage, then you can level shift to any voltage you want to interface with the ADC or whatever other applications you want. Okay. And what happened if these two resistors R3 equals R3 equal R1 and R4 equals R2? Okay. If R3 equals R1 and R4 equals R2, okay. And so we can plug this into this equation here, and V out equals minus R2 R1 V minus plus 1 plus R2 R2 R1 and times R4 equals R2, so we replace with R2, R3 equals to R1, we replace with R1, and R4 is R2, so it's like that. So V plus, okay. And V out equals minus R2 R1, V minus plus, this is R1 plus R2 times R2 R1 plus R2 times V plus. And this is cancelled. So V out equals minus R2 R1 V minus plus R2 R1 V plus. Okay. So what we get here, we got the output voltage V out equals R2 R1 V plus minus V minus. Okay. So what this means, let's transfer this right here. So R2, let me see. Okay, we can see it better from here, but it's a little bit small. But so V out equals R2, R1 ratio between these two resistors times V plus minus V minus. So this is a situation you want to get the reference difference voltage, but you also want to amplify gain. Okay, you want to amplify the difference. You want to amplify the difference voltage from here. So that way you can just set these two resistors same. R3 equals R1, R4 equals R2. Okay, this is very useful in if you want to, for example, in current sensing or any situation you want to take the difference voltage, then amplify it. Okay, uh, and in summary, this differential OPAP circuitry is really not that different from a non-inverting inverting input circuitry with the reference voltage like this. The only difference is now we set this reference voltage with two resistors.